So we're going to declare this thing called V, the electric potential, also sometimes called the voltage. So if you just see potential, not potential energy, if you just see potential, we're talking about voltage. And voltage is equal to the potential energy that a test charge Q would feel from a bunch of other source charges, divided by that test charge Q. It's basically saying if I have a bunch of source charges over here, and I put a test charge over here, what I can do is I can say, well, I know I can figure out what potential energy this test charge Q would have because of the other source charges. And then if I divide away how much my test charge is worth, I get this very convenient number, which is just my potential energy per unit charge. So we can write that our potential energy, if I rearrange this a little bit, is just Q times V. And this is very similar to our perspective where we defined our electric field to be the force per unit charge. We said, I don't need to know what's there. I just need to know how strongly will something respond if I do put it there. So we're going to define it this way, and we're going to see a lot of interesting uses for this. This is the potential energy per unit charge, and the unit of potential, of electric potential, is joules per coulomb, and we have a special name for that, which is the volt. So 1 volt is 1 joule per coulomb. That means if I have a potential of 1 volt, if I know in some space that I have a potential of 1 volt, that means that if I put 1 coulomb of charge there, that it has exactly 1 joule of potential energy. If I have 2 coulombs, I have 2 joules, and so on. So it's associated with a point in space. It's associated with a point in space. So let's think a little bit about this. If our potential energy is Q times V, Q times our voltage, we can always set up kind of this idea like we did with conservation of energy, that the sum of our kinetic plus potential always has to be constant, that energy has to be conserved. What's interesting about this is that, unlike with gravity, is because of our Q, positive and negative charges do very different things. So let's say I have some region of increasing voltage, of increasing potential energy. So for whatever reason, over here is very high energy, is very high potential energy. Over here is very low potential energy. What are my charges going to do? Well, a positive charge, right? A positive charge is if you try to move it towards higher potential energy, its kinetic energy has to go down. So if you try to move a positive charge in the direction of increasing voltage, it will slow down. Just the same way as if I throw a ball up in the air, it's going to higher potential energy. It wants to slow down. Similarly, if I let go of a positive charge and it moves through decreasing voltage, it will speed up. So positive charges do what we expect. As you go to, basically as potential energy increases, kinetic energy decreases. As potential energy decreases, kinetic energy increases. Negative charges do the opposite, of course. And you can kind of think of a negative charge as a balloon, right? What happens when you let a balloon go? It goes up in the air. It goes to higher and higher potential energy, so we think, and it speeds up while doing so. And that's all because as a negative charge moves to higher voltage, it actually loses potential energy. So in this case, our potential, even though our voltage is going up, because Q is negative, our potential energy is going down. And similarly, a negative charge will slow down as it moves through decreasing voltage. So voltage is very much like gravity or like gravitational potential energy. But again, I want you to think of the fact that we now have both kind of like positive and negative objects, and negative objects always do the opposite thing. All right. So again, we can kind of think about this potential energy as being close to things that are positive is like a high voltage, is like a high potential. Close to things that are negative is like a low potential. But where is zero, of course? And we are usually free to set zero wherever we want. If I have some point charge Q, right? Well, I can take the potential energy equation and divide out one of the charges. And what I get is this thing. If I just have some positive charge sitting in space, it's going to put out a voltage that is equal to 1 over 4 pi epsilon naught Q over R. And again, think about it. If I put a second charge in there, if I put a second charge Q prime next to it, I just get the potential energy back, and then I get Q times Q prime, and everything looks good. So this potential extends all throughout space, and once again, we put our V equals 0 at R equals infinity. We put our 0 potential out at infinity. And just here are some quick graphs to show you what that looks like. So here's a positive charge, and this is a graph of voltage on the z-axis, or electric potential, and here is a negative charge over here. And what you can see is that as you go pretty far out, it flattens out and approaches 0, but right in the middle you get this little 1 over R spike. You get this little location of a positive charge or a negative charge. And just like before, right, things want to roll kind of downhill, so other positive charges will get pushed away. Here, positive charges will roll in. Negative charges obviously do the opposite thing that we expect. Okay. So this is going to be a really important equation for us, calculating potential using that. So take a moment, and I want you to calculate what is the potential at this point due to my other charges. All right, well, let's work this out. So from my first charge, we'll start with this negative boy here. We'll call U charge 1. So my voltage from number 1 is going to be 1 over 4 pi epsilon naught. The Q is -1 nanocoulomb, so -1 times 10 to the -9th coulombs, all over, well, its distance is 4 centimeters, and that's inconvenient. So let's write that as 0.04 meters. Of course, I happen to know that this 1 over 4 pi epsilon naught is really 9 times 10 to the 9th. So on top I get -9 over 0.04 meters. And I need to grab my calculator real quick to work this out because I didn't bring it with me. So we're going to go 9 over 0.04. And this is, negative 225 volts. So this is still V1. From V2, I'm going to get my K times 2 times 10 to the -9th coulombs, all over, well, in this case, we are 5 centimeters away. So we get, well, this again happens to be 9. So I get 18 over 0.05, which is 360 volts. So my total is, of course, 360 minus 225. Which equals 135 volts. And one way to think about this is that it's a positive amount of potential energy. That means that if I brought a positive charge here, if I wanted to put a positive charge here, it would take me some work to do so. That my positive charge is pushing away harder than my negative charge is pulling in. On the other hand, if I put a negative charge there, it would be very easy. It would want to just come there very naturally. All right. Now, what if we have a more complicated arrangement of charges? In general, our voltage is just the sum of all of our individual voltages. We can just add them up. And again, because this is a scalar and not a vector, adding it and doing integrals with it is substantially easier. So here we have a little ring, and I do want us to look at this ring real quick and try to do this out. So let's say I wanted to find the voltage at some point P out here. If I wanted to find the electric field, it would actually be somewhat more complicated, but because this is a scalar, I can do a pretty good job. So if we look at this little section of charge dq, and I've got some total charge q on this large ring, if I take a little section dq it's going to make a contribution to my voltage. It's going to make a contribution to my voltage of, 1 over 4 pi epsilon naught times, dq, however much the charge is there, divided by r. And now in this case, my radius, I happen to know, is just the square root of x squared plus a squared is this. And what's nice about this is I don't have to do any sines or cosines. I don't have to find vectors because this is not a vector. So if I want to add up, if I want to find my final voltage, if I want to add up the influence of all of these little bits of dq, right, it becomes fairly clear at some point that if I kind of move around my ring, I take this dq and this dq and this dq, the radius a of my ring doesn't change. My distance x doesn't change. And so actually nothing about my integral changes. My entire charge q is at some distance away from this. So my integral really, I kind of just integrate over my charges and end up with 1 over 4 pi epsilon naught q over this. I just end up with all my charge being that far away. So we'll go over that in class. And what's nice is that being able to do these integrals with voltage, which is a little bit easier, lets us find our electric field somewhat easier. All right, next time, so the big summary here is that we can calculate our potential energy from 2 point charges this way. If we just have one charge or an arrangement of charges, the potential per unit charge, or our voltage, is given this way with just 1 Q. And again, that's very similar to how we had a force with 2 Qs and how we had an electric field with only 1 Q. It's a very similar idea. So next time we do this, we'll talk about parallel plate capacitors, voltage and electric fields, and equipotential lines and the relationship to electric fields. Thank you very much.